On August 30, 2019, a Crimean amateur astronomer named Gennady Borisov discovered something that astronomers had only dreamed of seeing: the second confirmed interstellar visitor and the first ever interstellar comet. Designated 2I Borisov, this object wasn't just another rock, it was an active, fizzing snowball from another star system, giving us our first true sample of the building blocks of an alien world. Let's explore this together.
The interstellar visitor.
What truly sets an interstellar object apart? It's all about the math, and for 2I Borisov, the numbers were definitive. This visitor was clocked moving at an incredible speed of about 32 kilometers per second, or over 115,000 kilometers per hour relative to our Sun. This extreme velocity placed it on a hyperbolic trajectory, a path so fast and open that our Sun's gravity could only bend its course, never capture it. The key figure is its orbital eccentricity, calculated by NASA's Jet Propulsion Laboratory to be around 3.36. For comparison, a perfect circle is an eccentricity of 0, and anything over 1.0 is on a one-way trip out of our solar system. Borisov's number wasn't just over the line, it was a clear declaration of its alien origins. It came into our system at a steep 44-degree angle to the plane where the planets orbit, confirming it wasn't a stray from our own Kuiper Belt or Oort cloud. It was a true messenger from the void between the stars, a pristine artifact that had likely been traveling for millions of years.
6 hours to truth.
For astronomers studying 2I Borisov, the challenge wasn't just a single 6-hour window, but a frantic race against the clock that lasted for months. The truth had to be captured before the comet rounded the Sun and disappeared into its glare. The geometry of the solar system becomes a ruthless timekeeper. As Borisov headed towards its closest approach to the Sun in December 2019, its position in our sky grew closer and closer to the Sun itself. This shrinking solar elongation meant the window for observation each night became shorter, squeezed into the brief moments of twilight after sunset and before sunrise. Major observatories like the Keck telescopes in Hawaii and the Very Large Telescope in Chile had to schedule their precious time down to the minute, knowing that by early 2020, the comet would become completely unobservable from Earth for a period. Every photon collected was critical, because once it was lost in the Sun's glare, it wouldn't be seen again until it had traveled much farther away, becoming fainter and less active. This celestial deadline created an intense global campaign to learn everything possible before the window slammed shut.
Anatomy of an anomaly.
The real mystery of 2I Borisov wasn't flashing pulses, but a chemical fingerprint that stunned scientists. As telescopes gathered spectra of the coma, the gassy atmosphere around the nucleus, they found something completely out of place. A team led by Martin Cordner and Stephanie Milam at NASA's Goddard Space Flight Center used the Atacama Large Millimeter, Submillimeter Array, or ALMA, to probe its composition. They discovered an astonishingly high concentration of carbon monoxide, or CO. The amount of CO in Borisov's coma was between 9 and 26 times higher than in the average comet from our own solar system. This is a critical anomaly. Carbon monoxide ice only stays solid at incredibly cold temperatures, below -250 degrees Celsius. This suggests that 2I Borisov formed in an extremely frigid, carbon-rich region of its home star system, a place far colder than the Kuiper Belt where our own comets form. It was a pristine chemical fossil, offering a direct look at the raw ingredients available for planet formation in a completely different part of the galaxy.
The pulse mystery.
While 2I Borisov didn't exhibit rhythmic, unnatural pulses, it did provide a different kind of drama that, honestly, kept astronomers on the edge of their seats. It began to break apart. In March of 2020, as the comet was already heading away from the Sun, a team led by astronomer David Jewett of UCLA used the Hubble Space Telescope to monitor it. They witnessed a sudden, sharp brightening, an unexpected outburst for a comet already in retreat. A follow-up observation a week later, on March 30th, 2020, provided the stunning answer. Hubble's images clearly showed that a large fragment, estimated to be about 100 meters across, had broken off from the main nucleus. This event, a violent and chaotic pulse of activity, provided crucial data. It allowed scientists to estimate the size of the original nucleus to be surprisingly small, likely less than half a kilometer in diameter. The fragmentation suggested the nucleus was fragile, perhaps indicating a different formation process than that of comets in our solar system. This sudden act of self-destruction was a one-time event, a chaotic pulse that gave us a rare look inside a visitor from another star.
Red Watch, Mars's observatory.
When a celestial target gets too close to the Sun for Earth-based telescopes, the next logical step is to look for another viewpoint. Mars, with its fleet of sophisticated orbiters, represents a critical planetary science asset. While there was no formal Red Watch, the concept of using Mars orbiters as deep space observatories is a very real strategy. Missions like NASA's MAVEN, the Mars Reconnaissance Orbiter, or MRO, and the European Space Agency's ExoMars Trace Gas Orbiter are equipped with powerful spectrometers and imagers. In October 2019, S2I Borisov made its closest pass of the Red Planet. These spacecraft were in a unique position. The challenge, however, is immense. These orbiters are designed to look down at a bright, slow-moving planet, not track a faint, fast-moving comet against the blackness of space. Reprogramming them requires complex command sequences and carries risk. Though no major scientific papers were published from Mars-based observations of Borisov, its flyby served as a crucial fire drill, forcing mission planners at NASA and ESA to refine their protocols for targeting future interstellar objects, ensuring that next time Mars is ready to serve as our solar system's forward observatory.
Natural or engineered.
The question of natural or engineered became a hot topic in astronomy after our first interstellar visitor, 1I Oumuamua, was discovered in 2017. Oumuamua was bizarre. It was small, showed no cometary activity, and yet accelerated away from the Sun as if something were pushing it, leading to speculation from scientists like Harvard's Avi Loeb that it could be an alien artifact. Then, 2 years later, 2I Borisov arrived, and it provided a powerful dose of reality. Everything about Borisov screamed natural comet. It had a visible coma, a tail, and a chemical composition that, while exotic, was a plausible variation of the comets we see from our own Oort cloud. The presence of cyanide and diatomic carbon, the reddish color of its dust, and its eventual fragmentation were all behaviors seen in comets before. Borisov became the crucial baseline, the Rosetta Stone for what a normal interstellar comet looks like. It suggested that Oumuamua was the weird one, the outlier, while Borisov represented a population of natural icy bodies that are likely common throughout the galaxy, ejected from their home systems by gravitational chaos.
The evidence chain.
The story of 2I Borisov was built piece by piece through a global chain of evidence. It started with Gennady Borisov's initial detection on August 30, 2019, using his personal 0.65-meter telescope. The alert was sent to the Minor Planet Center, which quickly flagged its unusual trajectory. Within days, major observatories swiveled to confirm. A team including Polish astronomers Piotr Guzik and Michał Drahus used the William Herschel telescope and Gemini North telescope to obtain the first spectra, confirming the presence of a coma and the chemical signature of cyanide, proving it was a comet. Then, the giants weighed in. The Hubble Space Telescope provided ultra-sharp images of the nucleus and its fragmentation. The Atacama Large Millimeter, Submillimeter Array in Chile, in the hands of teams like Martin Cordner's, delivered the knockout punch, revealing the anomalous carbon monoxide composition. Every piece of data, from backyard photometry to radio telescope interferometry, was cross-referenced and logged, building an undeniable and incredibly detailed portrait of our second interstellar guest.
The decision matrix.
In planetary science, every major discovery passes through a rigorous decision matrix before it's accepted. For 2I Borisov, the first branch of the matrix was to determine if it was truly interstellar. This was settled within days by multiple independent orbital calculations from centers like NASA's CNEOS, all of which confirmed an eccentricity far greater than 1. The next branch was to classify its nature. Was it an asteroid or a comet? Early images from astronomers like Piotr Guzik showed a fuzzy, extended coma, a classic sign of outgassing. This was immediately confirmed with spectroscopy that detected cyanide, the smoking gun for cometary activity. The final branch of the matrix involved its composition. Was it like our comets, or something new? This is where the data from Hubble, ALMA, and the VLT became critical. The high carbon monoxide levels and the presence of atomic nickel, detected by a Belgian team, moved the verdict from a typical comet to a chemically exotic but fundamentally natural comet. Every claim was backed by converging evidence from different instruments and teams, the gold standard for a verdict the scientific world could trust.
December 8, 2019.
While the transcript mentions a future date, the real climax of the 2I Borisov encounter happened in late 2019. On December 8, 2019, the comet reached perihelion, its closest point to the Sun, still a distant 300 million kilometers away. A few weeks later, on December 28, it made its closest approach to Earth, though it was still 290 million kilometers from us. This period was the peak of the scientific frenzy. Every major telescope on the planet capable of seeing it was pointed in its direction, capturing an unprecedented amount of data. This is when the high-resolution images were taken, the strange chemistry was confirmed, and its dust properties were measured. The data collected in those weeks revealed a comet with dust grains that were different from our own, compact pebbles that suggested a violent formation history. The intense observation campaign during this time provided the bulk of what we now know, turning a single point of light into a detailed case study of an object born in another solar system, billions of kilometers away.
2I Borisov, redefining interstellar preparedness.
The flyby of 2I Borisov, our real-life visitor, has permanently changed how we prepare for the next interstellar messenger. The days of being caught by surprise are ending. The legacy of this encounter is a new set of protocols for rapid response and data sharing. Agencies like NASA and ESA have refined their procedures for flagging and confirming hyperbolic orbits within hours, not days. Furthermore, the discovery has supercharged the mission of upcoming facilities like the Vera C. Rubin Observatory in Chile. When it comes online, this observatory is expected to discover not just 1 or 2 interstellar objects, but dozens every year. The data from Borisov, especially its exotic chemistry, has given scientists a new playbook for what to look for. Planetary protection protocols have also been updated, ensuring that if we ever encounter an object that passes closer to Earth or Mars, we have a clear chain of custody for any potential biosignatures. Borisov was a wake-up call, transitioning the study of interstellar objects from a curiosity into a predictive, systematic field of astronomy. The encounter with 2I Borisov was a profound moment in science. It was the universe knocking on our door and handing us a free sample. Unlike the complete enigma of Oumuamua, Borisov was a reassuring message that the comets in other star systems, the very building blocks of planets, look a lot like our own, even with their exotic chemical twists. It confirmed that the processes that formed our solar system are likely not unique, but it leaves us hungry for more. What will the next visitor be like? Will it be another comet, a rocky asteroid, or something else entirely? Thanks to what we learned from this interstellar guest, we are more prepared than ever to find out. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Future Facts.